I am Hayata Yamasaki. We show a framework of learning with optimized random features that uses an exponential speedup by quantum machine learning without sparsity and low-rank assumptions. Quantum technologies toward realizing quantum computation are attracting more and more attention. This is because the quantum computation may achieve large speedups in solving problems such as integer factoring compared to conventional classical computation. But it is important to establish further solid motivations by clarifying its advantage in solving the problems that may have greater social impacts. In our information technology society, data processing in our daily life is supported by machine learning technologies working behind it. Quantum machine learning emerges as a rapidly growing field of research to speed up and scale up machine learning by taking advantage of quantum computation. However, to attain large speedups, existing quantum machine learning algorithms require restrictive assumptions on using a very sparse matrix or a very low-rank matrix. So careful justifications of these extreme assumptions were needed in these algorithms. In contrast, we show a framework of quantum machine learning using an exponential speedup without requiring these assumptions, and hence broaden applicability of quantum machine learning. In our work, we consider a common task in the field of machine learning called supervised learning. Supervised learning deals with the problem of estimating an unknown function to be learned from given n input-output pairs of examples of data. These examples are given according to some data probability distribution. We want to learn an estimate of the function to be learned within a fixed space called a model, so that the errors on average should be minimized to a desired accuracy. Random features provide scalable learning algorithms based on well-established learning methods called kernel methods and applicable to big data. Using random features, we can represent a nonlinear function to be learned as a linear combination of nonlinear feature maps, such as sine and cosine. The learning is achieved by sampling many features at random frequency parameters, followed by performing regression of coefficients by convex optimization. Conventionally, random features are sampled from a data-independent probability distribution, but this may require a large number of features for achieving learning. In contrast, recent work has proposed to sample features from a data-optimized probability distribution. The use of this optimized distribution can significantly reduce the required number of features and is indeed provably optimal up to a logarithmic gap. However, a problematic bottleneck arises from each sampling step from this optimized distribution, requiring an exponential runtime in data dimension per sampling as long as we use the existing algorithm. To overcome this bottleneck, we discover that we can use a quantum algorithm. Our quantum algorithm achieves sampling from the optimized distribution in as fast as linear runtime, and hence achieves an exponential speedup compared to any known classical algorithm for this sampling task. We can also combine our quantum algorithm with regression by a well-established classical algorithm called stochastic gradient descent to achieve the learning as a whole without canceling out our exponential speedup. The novelty of our quantum algorithm is to avoid sparsity and low-rank assumptions that have limited applicability of quantum machine learning, as I will explain in the following. The difficulty in sampling from the optimized distribution arises from the inverse of an operator. The optimized distribution is described by a weighted inner product of two functions on an infinite dimensional space of functions. This includes an inverse of an infinite dimensional operator. Since computers using bits and qubits cannot exactly deal with infinite dimension, we represent this distribution by a finite number of bits up to a small precision delta using a well-established way called fixed point number representation. For simplicity of our analysis, we may rescale the given data appropriately in such a way that this rescaling is equivalent to choosing an appropriate precision without rescaling. In this way, we represent a discretized version of optimized distribution as a weighted inner product of finite dimensional vectors that includes the inverse of a matrix. In the limit of good approximation, this discretized distribution converges to the original optimized distribution. By a linear algebraic calculation, we prove that sampling from this optimized distribution can be achieved by preparing and measuring a quantum state denoted by psi. For this state, we show that some parts are implementable efficiently using conventional techniques in quantum computation, such as quantum Fourier transform. However, the problematic part is an inverse of exponentially large operator sigma that can be non-sparse and full rank in general. If we could assume sparsity or low rank of sigma, conventional techniques in quantum machine learning would suffice to implement its inverse efficiently. But without such assumptions, implementation of this inverse would need exponential runtime. By contrast, our technique does not directly use the conventional techniques that require sparsity or low rank, but can still implement this inverse efficiently. Our technique can avoid the sparsity and low rank assumptions, since we show that we can decompose this non-sparse and full rank operator into efficiently implementable parts. To show such a decomposition, we observe the fact that a non-sparse part of sigma corresponding to a kernel function used in random features can be represented as a diagonal operator in Fourier basis. Using this observation, we can decompose sigma into addition and multiplication of quantum Fourier transform and sparse diagonal operators that can be implemented efficiently. As a result, we achieve linear runtime in sampling from the optimized distribution without sparsity and low rank assumptions. This achieves exponential speedup compared to any existing classical algorithm for this sampling task. We also remark that sigma cannot have good low rank approximation. So recent techniques of quantum-inspired classical algorithms assuming low rank are not directly applicable either. Our algorithm may provide following insights into designing fast algorithms for quantum machine learning. Firstly, our technique can circumvent sparsity and low rank assumptions, and this is useful for constructing widely applicable algorithms for quantum machine learning. Indeed, we show that our algorithm is applicable to learning with conventional kernels, such as Gaussian and Laplacian, in a reasonable parameter region, even though these kernels do not necessarily satisfy the sparsity and low rank assumptions in general. Secondly, rather than just assuming the data input model without discussing its implementation, our analysis explicitly clarifies technologies required for implementation. In particular, we argue that our input model is implementable feasibly and efficiently by using a binary tree data structure combined with quantum random access memory, or QRAM for short. To prepare this binary tree, we may need a classical pre-processing of n data with runtime of order n to count the population of data. But this is the same scaling as just collecting n data. Given this binary tree, the input state can be prepared efficiently. To access this binary tree, we may need QRAM that can load it without destroying the coherence. How to implement QRAM efficiently is clearly described by recent research in concrete experimental settings. With our results, we can motivate further technological development toward realizing such quantum memory devices in addition to those for quantum computers. Finally, since we apply quantum computation to a sampling problem, our algorithm can avoid overhead of estimating expectation values from many copies of quantum states. The existing classical algorithm estimates the description of the optimized distribution using matrix inversion and then performs sampling. In contrast, our quantum algorithm represents the distribution by amplitudes of quantum state psi. We never estimate its classical distribution, since the overhead of estimating amplitudes would cancel out the speedup. Instead, our speedup is achieved by just performing a measurement of psi, so that we can sample each feature per only single state preparation and measurement. In this way, our results discover an application of sampling problems to designing fast algorithms for quantum machine learning. Consequently, our results lead to a promising candidate of killer applications of quantum machine learning with broader applicability by avoiding sparsity and low-rank assumptions. Our quantum algorithm achieves an exponential speedup in sampling random features from the optimized distribution to achieve the learning with significantly small number of features. We can combine our quantum algorithm with classical convex optimization by stochastic gradient descent to achieve the learning as a whole without canceling out our exponential speedup. This opens up a route to a widely applicable framework of quantum machine learning that takes advantage of an exponential speedup. Our results establish a more solid motivation for further development of quantum technologies in the long run, since high-speed, large-scale machine learning will be eventually needed in practice. Considering major roles of random features in the field of machine learning, our quantum algorithm may also be applicable to other machine learning tasks. And our techniques for avoiding sparsity and low-rank assumptions are expected to be useful for designing further quantum machine learning algorithms that achieve high speed and wide applicability at the same time. I would be happy to discuss further applications to progress the field of quantum machine learning. Thank you for your attention.